This video looks at the Argand plane. Now, complex numbers can be plotted on the Argand plane. The real component is plotted on the horizontal axis and is labelled RE of Z, and the imaginary component is on the vertical axis and is IM of Z. Now, a complex number written as A minus BI is said to be in Cartesian form. And you can see on this Argand plane, I have represented some complex numbers. So 3 plus I is the same as a coordinate 3, 1, 3 across, 1 up. Negative 2 plus I is the same as a negative 2, 1, negative 2 across, 1 up. Looking at the examples, place the following complex numbers on the Argand plane. Now pause the video, have a go. I just did notice at 4 plus 2i, you will have to extend your real axis to fit that in. Okay, so have a go. So 4 plus 2i, 4 would be around about there, and we have to go up 2. So that would be our u, which is 4 plus 2i. 3 minus I, so across 3, down 1, this would be our v, which is 3 minus I. W is 3i, it has no real component, so it's sitting on our imaginary axis. That's w, which is 3i. Z equals negative 2 minus 3i, so across negative 2 down negative 3. So that would be our Z, which is negative 2 minus 3i. Now, geometric representations. The geometric interpretation of adding or subtracting complex numbers can be seen as the same process as the addition of vectors. Now, warning, don't confuse the imaginary number I with the horizontal unit vector. Okay, so be careful with that. But as you can see in these diagrams, I have the first one, my blue line here is Z1, my pink line is Z2. So down the middle, Z1 plus Z2 would be represented by that purple line. Okay. So exactly the same as what we would do with vectors, because we'd go either this way, Z2 plus Z1, or we'd go this way, Z1 plus Z2. I've done the second one is a subtraction. So blue is Z1, pink is Z2, and the purple would be Z1 minus Z2. You can see that's because we go across Z1, and then I've had to reverse the direction of Z2 because we're subtracting it. So you end up with your resultant down there. And also remembering that when we multiply by a constant, it's just a longer line. So your modulus is longer. Okay, so let's look at an example here. Let u equal 2 minus 3i and v equal negative 3 plus 4i. Use geometric addition to calculate z equals u plus 4i. So let's go to our Argand diagram. U equals 2 minus 3i, so across 2 down negative 3, that's my u. I'm going to put a dotted line in there. V is negative 3 minus 4i, so there's my v. Again, I'm going to put a dotted line in there. Okay, if I want to add these, I'm going to do it like I would my vectors. I'm going to move my v to be on the end of my u. So this, think about the arrows going this way. Okay, we know we have to go tail, head, tail, head. So my v was a cross 3. So I have to move this way, 3, 1, 2, 3 to this point, and then down 4. So moving down 4. That would be where my v would sit. So it was at the end of u. So that means my addition is there. So that vector there, or that complex number there is u plus v. So that is negative 1 minus 7i. Let's check it. Z equals u plus v is 2 minus 3i minus 3 minus 4i. Bring our real parts together and our complex parts together. 2 minus 3 is -1. -3 minus 4i is -7i, which is what I had. Okay, and that was z. So I should write z, which equals u plus v. That's geometric representation. This video looks at the multiplication by I in reference to a geometric representation on an Argand diagram. So if we had z equals a plus bi, as you can see here, and we times by I, we'd have a plus bi, which would be ai plus bi squared. And we know that our I squared is equal to -1, so that gives us negative b plus ai. Okay, so our a and b is swapped over. If I times by I squared z, then I have I squared a plus bi. I squared, I personally would go from here to here. I squared is equal to -1. So everything is multiplied by negative. So that's -a minus bi. If we have I cubed z, then you can see that expansion, which gives us b minus ai. So let's put this into perspective. If I started with z equals 1 plus 4i, if I went iz, that would be I bracket 1 plus 4i, which is I plus 4i squared, which is I minus 4, or -4 plus I. So you can see that that's the coordinate -4, 1. I started with the coordinate 1, 4. This is what's represented on this Argand diagram. So you can see that 1, 4, and when I multiplied by I ended up at -4i. Sorry, -4, 1. Okay, if I multiply by I again, so if I do I squared z, that would be I squared 1 plus 4i, which is -1, 1 plus 4i, which is -1 minus 4i. If you think about that as a coordinate, it's -1, -4. So you can see I've moved down to -1, -4. So that's when I multiplied by I again. Multiply it by I again, and I end up at 4, -1. Multiply by I again, and I end up where I started with. So multiplying a complex number by multiplying a complex number z by I is equivalent to performing a rotation transformation of 90 degrees in an anti-clockwise direction about the origin. Okay, I'm moving in an anti-clockwise direction 90 degrees each time. So let's look at an example. If z is 4 plus 2i, graph the following complex numbers on the same Argand plane. So z equals 4 plus 2i. So on the Argand plane, that's equivalent to the coordinate 4, 2. So that's there. 4, 2. And I can put my line in if I want to. Okay. If I've got iz is going to be I 4 plus 2i, which is 4i plus 2i squared, which is 4i minus 2, or -2 plus 4i. So my coordinate is -2, 4. So -2, 4 is there. And you can see that 90-degree angle there. Okay. So I'll label them z equals 4 plus 2i, and this one is iz, which equals -2 plus 4i. Go again. I cubed z is going to equal I cubed times 4 plus 2i, which is 4i cubed plus 2i to the power of 4. 4i cubed, knowing that that is 4i squared times by I. So that's negative 4i. This is going to be plus 2i squared all squared, which becomes positive. So that's plus 2. So this is 2 minus 4i. And as you can see, I'm down there. 2, negative 4. And you can see that straight line as well. So this is I cubed z, which equals 2 minus 4i. So I could have done the geometric representation without actually doing the algebraic method. Okay, you'll also notice this straight line here. Okay, they're identical. Negative 2 plus 4i, if you think about it. So you've got iz, which is negative 2 plus 4i. You've got I cubed z, which is 2 minus 4i, and they both lie on the same line. So now we're going to look at graphing complex conjugates. Now recall that the conjugate of z equals a plus bi is z bar equals a minus bi. Now when graphed on the Argand plane, the conjugate is a reflection of the original complex number of z in the real axis. So if I've got 4 plus 3i, so z equals 4 plus 3i, the conjugate of that is going to be 4 minus 3i. So when we go to our Argand diagram, you can see that that's down there. So this is z bar equals 4 minus 3i, and you can see that that is a reflection in our real axis. If I have negative 3 minus 4i, I'll call this w, equals negative 3 minus 4i, our conjugate is going to be negative 3 plus 4i. So going to our Argand diagram, we're up there. This is w equal, our conjugate, negative 3 plus 4i. Okay, and that is a reflection of negative 3 minus 4i. So given z on the Argand diagram, sketch zi and the conjugate of z as vectors without calculation. So this is using your knowledge without actually doing any calculations. Personally, I would go for the conjugate first because that's a nice easy one. Conjugate is the reflection, so I have to try, do a dotted line up, and I have to try and get this distance, this y distance, the same, so it's about there. So that would be my conjugate. Now, zi, so I should write that, my conjugate is a reflection on my real axis, and my zi is a rotation 90 degrees in the anti-clockwise direction. Okay, so I need a 90-degree angle, and you might have a piece of paper or something that you can kind of help yourself to get that 90-degree angle. Or if you carry a protractor, that might help you as well. That's not too bad. So that's a 90-degree angle. Think about your X and Y's, or your real and your imaginary, your horizontal and vertical components changing. So that means this distance here is going to become my Y distance there. Okay, and my Y distance, use a different color, this Y distance has to become my X distance. So you can see that I'm approximately there. The other way to think about it, the length of the line has to be the same. Okay, that length doesn't change. So that would be ZI.